First of all, thanks to the organizers for inviting me, of course. And this is not purely an experimental talk, although I tried to. I was also asked to give a little bit more of an introduction. We've heard a lot about Casimir physics today already, but nonetheless, let's just start with some overview. Okay, this also doesn't work. So a little repetition. And what I would like to give here is a small morphology of dipole interactions, and this is with respect to distance. And at very small separations, what you have is something that we've heard about today, van der Waals interactions. And I agree with Francesco actually about the convention that actually van der Waals interactions are only between distinct dipoles, which most of the cases means atoms or molecules. And what we are talking about here are induced dipoles. So it's not fixed dipoles, but just induced dipoles. And the source for these interactions are, of course, vacuum fluctuations. And the same source you also have for extended objects like parallel plates. And you have this characteristic dependence on distance A in this regime. And it's important that everything here is non-retarded, as we have heard already. Then if you move to slightly larger separations, then you end up in a different regime, which is mostly referred to as Casimir or Casimir-Polder regime. Why? Because here you have retardation, and the distance is so large that these interactions, they are simply too small to be practically measured. I mean, there are some measurements at small separations, but it's very hard. So here you mostly have extended surfaces, and you have a change in the distance dependence. You see here you get an additional exponent here due to the retardation. And if you go then to even larger separations, then you end up in this so-called thermal regime here, where most of the interaction is not anymore contributed by vacuum fluctuations, but by thermal fluctuations, at least at room temperature. Of course, this depends on the temperature. Well, the border between the two regions here is, of course, not sharp, but you can draw a line here around the thermal wavelength, which is around 7.6 micrometers at room temperature. I will be talking mostly about this regime here and this regime in this talk. And I also want to reintroduce the Lifshitz theory, which we have seen quite a few times already. It's an old theory. So Lifshitz derived this for the first time for the energy per area between parallel plates at zero temperature in 1956, actually. It's a simple most configuration that you can have two parallel slabs here with dielectric functions. What is important here is that we have, as we have heard also, an integral that goes from 0 to infinite about complex frequencies because the dielectric functions here are indeed functions of complex frequency. And since you cannot measure this directly, you need to apply a so-called Kramers-Kronig transform to get it. Here, the epsilon of complex frequency is a function of the imaginary part of the dielectric function of real frequency. And this is something that you can measure indeed, for example, using ellipsometry and from the optical constants of your material of choice. So for gold, for example, it looks like this. This would be in the optical range. And of course, here you can see in this integral that the major contribution comes actually from omega equals 0. This is true both for thermal and for vacuum fluctuations. And so you need to extend this somehow to 0. You can measure it also at lower frequencies using, for example, capacitive measurements, but you can never truly go to 0. So you need to extrapolate. And this is done by one of these two models normally, which we have heard about today a lot already. They are both not first principle models, but they're very simple, effective models. The only difference is that Drude here has this additional factor that accounts for relaxation of the electrons or dissipation, actually. Now, the Drude model is very well known from material physics, where it explains a few effects like Johnson noise or the non-vanishing electrical resistance of metal at zero temperature very well. And the plasma model, strictly speaking, is only valid for an ideal electron gas at high frequency. So you would expect intuitively that the Drude model is the correct one. But then if you look at experimental data, and this is actually one of the best data sets that we have around. I stole this graph from a publication from Giuseppe Bimonte and Riccardo Decca. What you see here is the difference between theory and experiment, and the black curves are the 3 sigma deviations or error bars basically of the experiment, and you see that only the plasma model is in agreement with the experiment, while the Drude model is excluded to in total more than 99%. However, at large separations, actually it's not so sure. So we don't actually know what's happening here, because obviously the Drude model fits better here than the plasma model, but here we are very close to the experimental errors, so we actually don't know. So the data clearly suggests that we do not have dissipation for vacuum fluctuations at 0 frequency, but the situation at large distance is still unclear. And if we ask about the physics, we have to bear in mind that these are not first principle models, they are effective models. So none of them can be a real description of a metal. So whatever you do with these models can only be an approximation. But as I said, the DC dissipation, for example, is only captured by the Drude model, so it should be in some sense the more physical one. Okay, so why is this still worth to be investigated? There has been a discussion in the literature for more than 20 years now, and this is also why this has gotten the name Casimir puzzle, actually. There are other puzzles connected with similar differences between the models, but I will not talk about those. So why is this still worth to be investigated? For some, this is a test of the fluctuation dissipation theorem, which is a very fundamental theorem, and what we see here is actually against it, but I would not jump to conclusions too early. For some, it's also that you need to have non-local extensions of the Drude model. Indeed, there are some proposals, and they bring the Drude model again in agreement with the experiment. And it might also indicate there are different responses of materials for propagating and evanescent waves. Whatever happens here, we just don't know at the moment. Experimental evidence is not enough. So the next point is then thermal Casimir forces. We have also heard about that today, this time in thermal equilibrium. So when you want to have a T unequals 0, then you go, of course, from the energy to the free energy, and you have here the Gibbs distribution function. And it turns out, and if you want to have details, you can ask, for example, Francesco, that you can get from the 0 temperature expression the one for finite temperature by simply replacing this integral over frequency that I've shown you before by this sum here over the Matsubara frequencies, plotted here again, and that gives you again a very simple expression for the TE and the TM modes for the total renormalized free energy. Okay, the important part here, because we have heard about this already, is that you can split this free energy expression into a part that comes from the T equals 0 vacuum fluctuations and the part that comes from the thermal contribution, so just from Planck photons. And if you look at the second part in more detail, you can plot this, and you see that, as I've said before, at small separations here, the relative contribution of the thermal photons is very small. So in the range where most of the experiments happened, actually you just have more or less vacuum fluctuations. Only at larger separations, most of the Casimir force is given by thermal photons. So this is also the range where we actually don't know what's happening between the two models. And so the idea would naturally be to measure in this range. But the problem is that the force or the pressure there is very, very small. Too small for most experiments. However, this would be possible to measure with parallel plates. And why, I will explain you in a second. But before that, let's look at some other options where we could see differences between the models. And this is now considering two half spaces at different temperature. So you are out of thermal equilibrium. And then it turns out, as has been first computed by Antezza and others, that you have the average of the equilibrium temperature contributions plus a non-equilibrium term, and this is now the new thing, and this is a term that is anti-symmetric under the exchange of the temperatures between the plates plus radiation pressure. And this non-equilibrium term here that vanishes if you have identical scattering matrices on both objects. So that means in order to trigger it, you need to have either different materials and or different thicknesses. Okay, but that's not the situation you have in an experiment. In an experiment, you have a heat bath all around your objects. So that is a different situation, and that leads to a switching of the sign here in the radiation pressure part. And when you then compute your total Casimir force that you expect between parallel plates, you actually see here that you can get an attractive regime, and a repulsive regime. So that this is yet another way in order to have repulsive forces. And of course, this comes mostly from the switch in the radiation pressure. So strictly speaking, it's not Casimir forces, it's radiation pressure, but still this is very interesting. What we've heard also in the previous talk is that there are many ways to tune the dielectric functions, and together with the non-equilibrium term, you can have repulsion here, you can have spatially oscillating potentials depending on the geometry, you can have bound states even, as we have seen, levitating things, and you can have, there's something missing, self-propulsion. The self-propulsion is mostly actually due to the latter part, radiation pressure. It's the same effect as you have heard for the Pioneer anomaly, basically, but then for smaller objects. So there's a wealth of physics to be discovered here with these non-equilibrium interactions. And for us, the question is, of course, can we measure that? And first of all, I want to say, yes, this has been measured. The non-equilibrium term has been measured in 2007 by a group around Albrecht. But in this experiment, they worked with a Bose-Einstein condensate, actually. The error bars were so large that they can only do a qualitative measurement. But what we'd want to do is to have a real quantitative measurement in which we can also distinguish between truth and plasma. So now I want to motivate why we are choosing parallel plates for this. Most of the experiments that have been conducted were in this geometry between a sphere and a plate, with some exceptions with microbeams where you can explore more difficult geometries. And the reason for that is simply that people wanted to avoid parallelism because it's pretty difficult. If you look at the sensitivity here of these experiments, with the micro-machined oscillators, we can get to actually femtonewton resolution, which is very impressive. But we have to consider something else here. It's not the total sensitivity that counts, but it is the sensitivity per force generating area. Why is that? Because if you have an interaction that depends on the separation between your objects, then your actual force is generated only by a tiny patch near the point of closest approach. So despite having a large object, you lose a lot and you have very small generated forces. On the parallel plates, on the other hand, you use the entire surface in order to generate your force. So even with a mediocre absolute sensitivity here, you use the geometry in full, and so your sensitivity per force generating area can be much higher than for all the other experiments. So you get several orders of magnitude improvement here. That brings me to the setup that we have. It's called CANNEX. This was the setup that we used 2018 for the proof of principle. What you see here is just a huge vacuum chamber that serves for isolation against seismic and thermal influences. The actual experiment hangs here on a pendulum inside a smaller vacuum chamber, and the actual experiment is just this small part here. If you look at this part, it's very simple. You just have just two plates. One is a mass spring system in parallel to another plate. This mass spring system here actually looks like this. It's spiral-shaped springs with a central disk of 1 square centimeter. So this is really macroscopic. The Q factor, by the way, is around 15,000. So that is much higher than the 150 that we heard in the previous talk. This is a photo. It's all etched from a silicon single crystal. And the lower plates, they are actually just glass cylinders put upward. And one of the most important characteristics here is that everything needs to be really flat on all scales. So you see here, this is really flat on a few nanometers over the entire surface. For the proof of principle, we tried to measure forces and force gradients at the same time. This is possible because you can measure the extension of this sensor, and you can measure the shift in the resonance frequency. By measuring forces and force gradients, you can balance your systematic effects and also exclude a few. For the parallelism, at that time, we used a capacitive scheme that had quite some disadvantages. This is a photo of the prototype with shielding removed, just that you see that it was real. The first data set that we got was not very good, actually. Casimir forces are down here, and we had a parasitic AC potential that was getting into the setup, and for this reason, the actual data was taken up here. But nonetheless, despite a lot of technical problems, we could prove that we can approach with these parallel plates the separation range that we wanted, and that we can get a decent sensitivity here. So the proof of principle was successful, and since then, we've spent a lot of time improving the setup, getting more money for it, and currently it's being rebuilt actually as a new project. The improvements that we have done are, first of all, we kicked out the capacitive bridge here because it gave us a large electrostatic background. So we are now measuring distance and parallelism with additional interferometers. The second thing is that we implemented a thermal control system that can basically control the temperature of this sensor plate without contacting it. It goes just via radiation. That is possible due to the transmission properties of the silicon plate here, that you can directly control everything within 1 millikelvin precision. That's necessary to get the necessary force resolution. And at the same time, we want to have 10 Kelvin difference between the sensor plate and this lower plate here. We also took a lot of precautions against electrostatic effects. So we are having an argon ion gun and UV LEDs here in place so that we can clean the surface from any chemical or otherwise disturbances that would generate electric patches here in situ. We can also measure that by some Kelvin probe that I have not shown here in this picture, but we will characterize that. This is a rendering of the current design that we have that is being built. I will not go into too much detail. And this is the result of a simulation with the full design that we have and with feedback circuits in place. And you see here that the total deviation from the targeted temperature on the sensor plate is just 0.4 millikelvin. On the lower plate, it's a bit more difficult because it's an extended object. So in our first try, we had 75 millikelvin, and with some precautions, aluminum coverings and so on, we got to 2.2 millikelvin deviations of the entire surface temperature from the set point. Our goal is, as I've said, 1 millikelvin difference on each surface while having 10 Kelvin difference between the plates. So also on the vibration isolation, we improved a lot. This is designed with a two-stage system. We're using here non-linear mechanical elements. These are inverted pendula and geometric anti-springs. This is technology that has been developed actually for gravitational wave detectors, and we are using it quite successfully. The initial idea was to put the setup at our institute here in Vienna, the Atom Institute. But what you can see is that directly in front of the institute there is a runoff of a highway, and there are also some subway lines here. So the seismic background, which you can see in these graphs here for horizontal and vertical direction in gray, are very high. And what we can tolerate are these red lines here, and you see here around the resonance frequency of our sensor, this is pretty low, so we would need to decrease the seismic background by 3 orders of magnitude, and for this reason we have developed a two-stage system. But it turns out this is not the only solution. Very recently we decided to go from Vienna 50 kilometers towards the Alps into something that's called Conrad Observatory. It's a seismic and geomagnetic observatory inside a mountain. And there, the seismic background, here the black curve, is much lower, actually by more than 2 orders of magnitude. So we will place the setup there. And then a one-stage system giving you the green line will be enough. So this is a bit cumbersome to get there, but it's much better for the experiment. We have also done a lot of metrology. We have computed a complete error budget. And without going into further detail, I will show you the budget. The previous setup is, if it would have worked as designed, then it would have been here, this dashed yellow line, which is hard to see, obviously. And the new setup would be at the yellow line that we have here. To make it more simple, the targeted sensitivity for the pressure is 1 nanonewton per square meter, and for the pressure gradient, 1 millinewton per cubic meter at around 10 micrometer distance. The most important characteristics that disturb us are electrostatic patches, still, and corrugations, meaning deformations of our surfaces. At larger separations, this is basically a statistical limit for the time that we have planned here detection, so this could be lowered down to this curve. And what you also see here is the Casimir force. It's the black line. So you see this is more than 2 orders of magnitude above the error for all distances that we have here. So this will be a very accurate measurement. But what we are particularly proud of is actually that we can also measure here in gray the gravitational interaction between the 2 plates. This is very interesting for other communities because it is in a completely new regime here. Okay, so what can be achieved? This is a signal-to-noise ratio plot for Casimir forces. Now we have plasma, Drude, and also the non-local extension of the Drude model. And you see current experiments are near 1 in this regime. And with CANNEX, we could get to a few hundred. So it would be clearly possible to distinguish between these models also at very large separations. And we can do the same also at 10 Kelvin difference. Now, if we look at the predicted results for this non-equilibrium term here, the first thing that comes to my mind would be to measure the gradient, because then we don't have radiation pressure, which is independent of distance. But if we here insert our sensitivity, you see that the signal-to-noise ratio would only be around 2 for the plasma model, and the Drude model could not be measured. So we could also do the same thing for the pressure. Here, the deviations between not having these terms and having them is much larger. And you also see here, this is radiation pressure, and this is radiation pressure plus the non-equilibrium term. And if we put also here the sensitivity, you see this is much higher than the sensitivity. Signal-to-noise ratio at large separations would be around 5. So this is clearly measurable, and that means that using CANNEX, we can make a quantitative measurement of these effects even at just 10 Kelvin difference. Okay, I will skip now the other things. This is about dark energy and dark matter. We might discuss this if you are interested after the talk. And I will jump directly to the conclusions. So CANNEX is probably the first metrological parallel plate experiment measuring Casimir forces. We can at the same time detect the force and the force gradient between macroscopic plates in one measurement. We can also do interfacial and also Cavendish configurations, so there's a lot of measurement possibilities. The setup is currently being built up. We expect it to be ready early next year. So at the end of next year, we should have first results for Casimir measurements. And that means Casimir forces at larger than 10 micrometer, very accurate, also thermal effects, and a lot of dark matter and dark energy measurements as well. So thank you for your attention.